Hiya folks, in this video we're going to have a look at how you can determine the electric field strength at a point when that point is not acting in a straight line. So in this question we have ABC is an equilateral triangle of side 50 cm with a point A at the apex. At B and C are stationary charges of magnitude +2 millicoulombs. So part A of the question is asking us to calculate the magnitude and the direction of the electric field at A. So what we're going to need to do here with this question is first of all take the information from the question and put it into a diagram, and that will help us visualize what's going on, what quantities we know, and maybe what else we need to figure out. So ABC is an equilateral triangle of sides 50 centimeters. So that means that our triangle has equal length sides and that all those sides are 50 centimeters long. Now it also tells us then that the angle between each of the sides is the same. So each of these angles is equal to 60 degrees. We also know that A is the apex, so we'll label A here at the top. And then B and C are both stationary charges that have a magnitude of +2 millicoulombs. So I'm just going to draw a charge here, which is point B. I'm going to draw a charge here on the other side, which is at C. And each of those is +2 millicoulombs. So we want to calculate the magnitude and the direction of the electric field at A. So to do this, we're going to need to work out what is the electric field strength due to each of the two charges involved. And then once we know what that is separately, we can then combine them to work out what the resultant electric field strength is. So let's start with the electric field strength because of B. The equation that we're going to use here for the electric field strength because of B is that the electric field strength is equal to K multiplied by Q divided by R squared. So if we're looking specifically at what is the electric field strength due to point B, well then K has a value of 9 by 10 to the power of 9. The charge in question here is 2 millicoulombs, so that's +2 by 10 to the -3, divided by the separation. How far is this point A from the charge? And that is 50 centimeters or 0.5 meters, and it's squared, which gives us 7.2 by 10 to the power of 7, and that is newtons per coulomb. So that's the size of the electric field strength because of point B, but what we haven't included here is the direction. So I'm going to show the direction on the diagram using a blue pen here. And at the point A, that field strength is acting in the same line as the 50 centimeters, and it has a value there of 7.2 by 10 to the 7. So now let's work out the electric field strength because of the charge at C. Well, again, we're using the same equation here where we have K times Q over R squared, and actually when we look at the numbers here, the numbers are exactly the same because we have a +2 millicoulomb charge and it is separated by 50 centimeters from that point A. So what we find is that the electric field strength because of the charge at C has the same value as the one at B. The only difference here is going to be the direction that it's acting in. So we'll use a red pen to show the electric field strength because of charge C. So that's going to be acting in this direction. So we have so far worked out the individual field strengths because of each separate charge, but we need to figure out what is the overall electric field strength, what is the resultant field strength because of these two charges. So to do that, we need to work out what is the resultant of the two field strengths that we've just worked out. So in order to do that, we know how to add vectors together. We've been doing that since AS. So there's a few things I'll need to add into this diagram now that will be useful, and that is the angles. So let's draw on a line here at the top of the triangle, just a line to the horizontal. Well, we know that this angle between the blue line and that horizontal will be 60 degrees, and the same will be true on the left hand side. That will also be 60 degrees. From the center of the triangle, that means we have an angle of 30 degrees between each of these field strengths and the central line. So to work out this resultant, what we're going to do is work out what is the resultant horizontal components and what is the resultant of the vertical components. So looking at the horizontal first of all, what we actually see is that the resultant in the horizontal direction is 0, and that's because we're going to have 7.2 by 10 to the 7 cos 60 minus 7.2 by 10 to the 7 cos 60. Because they have the same value, they're at the same angle to the horizontal, but they're on the opposite sides of that equilibrium line in the middle. So that equals 0. If we look at the vertical, well then we have to work out the vertical components of each of these field strengths. So if we take the one in blue, first of all, we have 7.2 by 10 to the power of 7 cos 30. And that's resolving it into the vertical. Well, if we look at the other force, since it's also acting upwards, then we're going to add that on. So it's plus 7.2 by 10 to the power of 7. And that is also cos 30. So what we're doing then is adding those together. So we have 14.4 by 10 to the power of 7 cos 30, which is equal to 1.25 by 10 to the power of 8, and that is newtons per coulomb. So what we've just shown here is that the resultant electric field has no horizontal component, but that it does have a vertical component of 1.25 by 10 to the power of 8 newtons per coulomb. So that is our resultant, 1.25 by 10 to the power of 8 newtons per coulomb, and that is acting vertically, it's acting upwards from that point A. Now part B of the question, very short, but it says state without further calculation the magnitude and the direction of the force on a charge of plus 1 coulomb that's now placed at A. Well, the fact that it says without any further calculation should give you a clue that there's not much involved here. In fact, the answer is exactly the same. And the reason it's exactly the same, that's 1.25 by 10 to the power of 8 newtons per coulomb in the vertical, so acting straight up. So the reason that it's exactly the same is because that's what we define the electric field strength as. The electric field strength at a point is equal to the force that would be produced on a test charge of 1 coulomb at that point, or rather of a positive test charge of 1 coulomb. So that's really what they're testing there. They're testing to see, do you understand what is meant by the electric field strength? The fact that it is the force that would be felt by 1 positive coulomb of charge. So that's that question, and hopefully you found some of that useful.